Hi, this is Mrs. Kidman, and in this video, we are going to be discussing how we can use the composition of functions to evaluate different functions using their graphs, tables, and doing it algebraically. Now, in a previous video, we discussed how we can do it algebraically by talking about two different options. We discussed how we can compose the two functions and make a composite function, and then substitute in the value for x and evaluate it there. Or our other option is to evaluate it at the function that we're composing within the other function. So if it were something like f of g of x, we would evaluate in g of x, and then whatever that output is, we would put into f of x. Now that's very important, this second idea, when it comes down to evaluating with graphs and tables. So let's start by evaluating a few questions algebraically, and then using that idea of how we were evaluating them algebraically to then determine how we can use a table or a graph to also evaluate functions. Then we will discuss one quick word problem in which we might see the application of this, and that will help us understand the composition of functions even more. So what we want to do is use the functions below to determine the value of each composite function algebraically. So we've got f times g of 3, or g composed of h of x, h composed of j of 12, and h composed of g of x. So let's start here first with these ones that we are evaluating. So what we're going to do is we want to evaluate these. Now remember, f composed of g of 3 is the same as f of g of 3, meaning that what I can do is I can evaluate my function when g equals 3, and then whatever that evaluation is, then evaluate f of x at that number. So let's take a look at this here. So we've got g of 3, which is equal to 3 times 3 minus 2, or 9 minus 2, which is 7. So g of 3 equals 7. Then we can evaluate it in function f by putting 7 in there, and we've got 2 times 7 squared, or 2 times 49, and 2 times 49 is going to be 98. So that is what that function is evaluated at. Now let's take a look at h composed of j of 12. Now again, just like before, we know that that's going to be the same as h composed of j, which is composed of 12, meaning that what we're going to do here is substitute 12 into j, get out whatever our answer is, and then substitute that into the function h. So let's start there. We've got j of 12, which is equal to 6 over 12, which equals 1/2. And then we're going to take this value and substitute it into h. And so we've got h of 1/2, which is equal to 3 minus 4 times 1/2. Well, 4 times 1/2 is 2, so 3 minus 2, which equals 1. Okay, so using this idea of how we evaluate those functions algebraically, we're going to do that to determine how we can evaluate on tables and on graphs. Now, notice what we're doing here is we're saying when x equals 3, y equals something. And then we take whatever y equals and say when x equals something, then y equals our answer. Okay, so that question mark means something. That's our intermediate solution, and our star is what we're actually looking for. And that's how we proceed to evaluate these functions algebraically. We're going to do the exact same thing when we're evaluating them on a table and on a graph. So let's take a look at these tables with ordered pairs to determine the value of each composite function. So for example, we've got f composed of g at 36. So these are not labeled here, but this first one is f of x, and the second one here is g of x. So what we're going to do is we're going to say this is the same as f composed of g of 36. So what we're going to do is we're going to look at function g when x equals 36, figure out what y is, and then we're going to take that value and plug it into f of x to figure out what it equals again. So let's take a look here. So first we're going to look at when g equals 36. Well, this is g of x. When x equals 36, then y equals 6. Now that is this g of 36 part. So now we want to do that f of 6 part. And what we can do is come over here and look to when x equals 6 and see that our answer is going to be 21. And so f composed of g, when evaluated at 36, is going to be 21. Now, isn't that so much easier than doing it algebraically? What we're doing is that same process. We're taking what's on the inside and we're substituting that x value into our function there. So we're taking our g of x and we're looking at what happens when I put in x equals 36. And our output there is 6. Then we take that output of 6 and put it into f of x, the function we're composing it into, and see what that output is, and we get 21. So that is kind of how we're going to do this. Now let's take a look at this next one. This one is g composed of g of 16. Or g composed of g evaluated at 16. So first we want to look at g equals 16. Well, that's here. meaning that our output is going to be 4. So then we want to do g of 4 to figure out what that is. And as we figure out our output of 4, we come over here and notice it's g of 4 again. So we're going to stick with this function. We're going to go to 4 and look at 2. So what does this equal? 2. So g composed of g at 16 is equal to 2, just like how f composed of g at 36 is equal to 21. So we can kind of see how that pattern works. Now let's take a look at this next one here. This is g composed of f evaluated at 4. So g composed of f evaluated at 4. So we need to evaluate 4 in function f and then take that to g. So we've got 4. We're going to evaluate it and we get out a 1. Then what we're going to do is come over to our 1 here and evaluate it and put it over here. So what is that going to end up equaling? Well, this one is going to be a 1 because that f of 4 turns into a 1 and g at 1 is equal to 1. Awesome. Okay, let's take a look at one last example here. Hopefully you're getting the hint on this. So we evaluate it in the second one, just like we did before, and then put that one into the first one. So f of 4, or f of 4. So what we're going to do for this one is we're going to look at when f of x equals 4, or when we put 4 into f of x. So that's going to be this one again. And our output here is 1, right? But now I'm going to put that back into the function f, which is this one. And our output here is going to be a negative 14. So again, notice how we have these two same functions, but we can use those different routes to then evaluate it. So it's a super cool method in order to evaluate these composition of functions when we have their tables, because we can substitute it into whichever function comes first and then use that output as the new input in whatever function we're evaluating it in second. So it follows along with that second method that we talked about previously, and it's awesome. Now, when we do graphing, we're going to do the exact same thing. So remember, h composed of f of 3 is the same as h times f of 3. So we're going to look at function f here, which is in blue. We're going to go to when x equals 3, and that gives us an output of negative 4. So then we want to do h of negative 4, which this is function h. If I go to negative 4 here, it crosses right at this point, which equals 5. Okay, now let's take a look at another example here. This one is going to be f composed of g evaluated at 4. And so we're going to go to g is 4, and we're going to see that it crosses right here at 2. So now we want to do f of 2. And when I look at function f at 2, we end up getting negative 3 for that answer. Oh, that circle didn't turn out. Okay, so let's take a look at another example here, just like we did before. We're running through this process over and over, but you can see how it's very similar to when we use the table. So this f composed of f at negative 4, f composed of f at negative 4, we start here by looking at what happens when we do f of negative 4, so that piece on the inside. So f at negative 4 becomes negative 5. So now I want to figure out what happens when I get f of negative 5. And if I do f at negative 5, we get negative 6. Awesome. Okay, 2 more examples here. G composed of g at 1. So we're going to look at g and go to 1, and we can see, so g composed of g at 1, we can see that g of 1 on the inside here is equal to 0. So then we want to evaluate g again at 0. And as I put g at 0, we end up getting an answer of 2. Okay, our very last one here is g composed of h at 0. So we're going to look at function, so g composed of h at 0. And so we're going to look at function h when it's at 0, figure out what that is, and then evaluate g at whatever that output is. So h of 0 is going to be 5. So this equals 5. So then what we want to do is evaluate what happens when g equals 5. And as we go to graph g here and look at 5, it ends up being right at 0. So that is how we can use a graph to determine it. So it's really awesome that we can do this composition of functions, because really what it is it's saying I'm going to evaluate in this function, followed by this function, followed by this function. And we can actually do a chain of these functions as long as we want. So let's take a look at one last example here. This one says, a salesperson sells shoes part-time at Super Shoes in a South Street mall. She earns a 2% commission on total sales over $5,000, which is paid as a bonus at the end of the year. Let her total sales be represented by x. If f of x equals x minus 5,000 and g of x equals 0.02x. Between these two functions, f of x and g of x, which one would calculate her bonus at the end of the year? F composed of g or g composed of f? So we have to think of it this way. We've got f when we evaluate g of x, or g after we've evaluated f of x. And we need to decide, well, let's look at our two functions here. F of x in this case is representing the amount of money that has been made. And g of x represents our commission amount. So which one comes first? Well, we need to know how much money is made before we can determine our commission. So in order to calculate it, what we want to do is figure out money made first. Now, remember when we evaluate them, we always do what's on the inside first. And so in order to do this, we actually want to use this function g composed at f of x. And the reason why is because think of when we evaluate, if we rewrite that f of x is on the inside, meaning I have to evaluate f of x first. And that's true. We need to determine how much money we've made before we can determine how much commission money we get. So using this idea, let's then figure out how much her bonus is if she sold $9,172 in shoes this year. So we're going to use this composite function here. So we've got g times f of x. Now using this, let's calculate her bonus. So we want to start with this inside here. So we're going to start by doing f of 9,172, or I'm going to figure out how much money she made minus that commission. So that's 9,172 minus 5,000. And as we substitute that in, what that'll end up simplifying to is $4,172. So that's how much she made over that 5,000. Now that we have this, we need to plug that number into our G, and we need to do find 2% of that 4,172. Now, as we go in to calculate that 2%, what we end up getting is this is going to be about $83.44. So you can see that we end up getting a commission of about $83, which is awesome for her just doing her job. But notice how we had to calculate that f of x first before we could figure out what that commission was, because we needed to know how much money was made. And that, in a nutshell, is how we can do composites of functions. Now, like we said previously, we can actually compose more than just two functions. So we could end up, if we had something like f of x equals 3x, g of x equals 7 and 7x plus 2, and h of x equals x squared, we could actually compose these, and we can compose them as many times as we want. So sometimes you'll end up seeing these composition trains or chains where it's like f is composed of g, which is composed of h, which is composed of h, which is composed of f, which is composed of g of x. So what is this, or of x, or of a number like 1? So then what does this mean here? Well, this means that I'm going to evaluate each of these starting from beginning to end. So we've got f. We've got f is composed of g, which is composed of h, which is composed of h, which is composed of f, which is composed of g of 1. And then we have all of our parentheses for each one that we have there. And then we can evaluate it. So we start with the most inside here, g of 1. And so as we're evaluating g at 1, we would say 7 times 1 plus 2 equals 9. So now that we've evaluated g at 1, then we would look at what happens when I put 9 into f of x. Well, we do 3 times 9, which equals 27. So we've gotten rid of this part. Now we're evaluating this section, and we evaluated that to be 27. So then what we want to do is evaluate the next section here. So what happens if I put that 27 here? And we can continue on going and going until we've completed our chain. So it's really cool how we can do this composition of functions. It's not just one function, but we can compose as many functions as we want and then use those functions to evaluate. So that is your assignment, is to evaluate a long composition of functions. We have this crazy chain activity. If you have questions, feel free to reach out, but that is the composition of functions there for you. We can do it in a table, we can do it on a graph, and we can do it algebraically. But compositions of functions are so helpful, especially when we think about some of those applications of the real world. If you have any questions, feel free to reach out, but that is composition of functions part 2.